Bismillah ar-Rahman ar-Rahim. Today we have a very interesting subject called sequences. Okay, we have sequences and series. These are two topics in mathematics of interest. We will start the first one today, which is called sequences. Now, so what is a sequence? Simply, we can say that a sequence is a list of numbers, readings, written in a definite order. So, assume we are taking readings. So we say, this is my first reading, A1. This is my second reading, A2, and etc. So we have these are numbers thrown here, like A3, but with a definite order. So we have, for example, this is the nth reading, and etc. This is called infinite sequence because we have a sequence with infinite number of readings. What is our target here is to understand the meaning of convergence and divergence of sequences. What does it mean convergent sequence? What does it mean divergent sequence? Before we go to that, we have some notations. So I just denote this sequence. This is a notation for sequence. Sorry for this. This is a notation for sequence. So what is the notation for sequence here? What is the simple use for sequences? Usually we denote this in a set notation, so sometimes we use like something like this. We say this is A1, A2, A3, so we list some of the elements at the beginning, and then we say this will go up to infinity. Okay, this is an infinite sequence. Or it is denoted by this. Sometimes we just write like, we find the nth term, formula an, and we just write here, this is running from 1 up to infinity. So it's A1, A2, A3, A4, etc. So sometimes we use this listing elements notation. Sometimes we use this compact form of the sequence. But at the end, this is representing a sequence. This will also represent a sequence. To take an example of this, assume we have the following, just example about the notation here. Assume we are given that the sequence is given by n over n plus 1, and this is from n equal to 1 up to infinity. Now, can we move and find some few terms of the sequence? The first, let us say 3 terms of the sequence or 4 terms of the sequence. How to find the first few readings of the sequence? Simply here, you just substitute n equal to 1. So if you substitute n equal to 1, you have 1 over 2. If you substitute n equal to 2, that is 2 over 3. And if you substitute n equal to 3, you have 3 over 4, and so on. So these are the first 3 elements in the sequence. So you can move from this notation to the other notation. Another example, another type of sequence, we have, for example, here minus 1 to the n times n plus 1 divided by 3 to the power n. Okay, if we are interested to find few terms of this sequence, the first 3 terms, 4 terms of the sequence, we just substitute. This is n equal to 1 up to infinity. So if I substitute 1, for example, I will have here minus, so minus sign, 1 plus 1, that's equal to 2, so it's minus 2 divided by 3 to the power 1, that's equal to 3. And so on. You just substitute the next integer number, positive integer number, which is 2. If I substituted 2 here, I get minus 1 to the power 2, that is positive. And this is 2 plus 1, which is 3, divided by 3 to the power 2, that is 9. Or simply you can simplify this and write only 1 over 3. Okay, fine. Next, I substitute n equal to 3, so this will be negative, so that is minus 3 plus 1, that is equal to 4, divided by, we have here 3 to the power 3, that's equal to 27, and etc. So this will continue like this, and we have what we call infinite sequence. So this is how to move from one notation to the other. And how to find some few terms of a sequence given its nth term. This is called the nth term of the sequence, or the formula for the nth term of the sequence. Okay. What about the other way around? If I give you some listings, I'm listing some elements of the sequence, and I told you that this pattern will continue. Try to find the general form of the sequence. That is interesting also. Okay, so let us do that. So let us take an example, moving the other way around. So let us say this is another exercise says, okay, in that exercise, let me say here, list, since we decided to find only 3 terms, so let us say list the first 3 terms of the given sequence, Okay, so this is what we have for the first exercise. Now we are moving backward. Say, find a formula for, let us say, the general term or the nth term. Let's call it an. Okay, of the sequence. And now what is the sequence given here? We have the sequence given by this. It is 3 over 5. Okay, then the first reading. The second reading is minus 4 over 25. Then the third reading is 5 over 125. Then the next one is minus 6 over 625. Next one is 7 over 3,125, and etc. Assuming we keep the same pattern. What will be the nth term? So I'm assuming this. Assuming this will continue. This system will continue the same, okay? This is what we have. This is continuous. Okay, so this pattern will continue like this. So what will be the nth term? Let us try to now make a matching between the natural numbers, so n equal to 1, and the first element, a1. Now, what is the 3 over 5 if you just use n equal to 1? Then I move to the second one, n equal to 2, and I need to make a matching with the second element here, and so on. And then I can generalize this. So what is a1? a1 is equal to what? 3 over 5, okay? And what is a2? a2 is equal to minus 4 over 25. So let us see now. N equal to 3. N equal to 3, a3 will be equal to 5 over 125. So I can see now 3 things are moving. The positive minus sign, plus, minus, plus, minus, plus, minus. You can see it from here. Plus, minus, plus, minus, plus. So next one would be minus. So I need to take care of this. So I will try to generalize these readings to be as follows. I have minus 1 to be controlled. I need to observe that the odd terms are positive, the even terms are negative. So it's supposed to be minus 1 to the power either n plus 1 or n minus 1. I need to move it. So once I substitute here an even number, I will get an odd number. So this will be negative. And I substitute here odd number. So the addition will be even. So this will be positive. So that's controlling the minus plus sign. What about the denominator? Look, here we have a1, that is 5 to the power 1. Here we have a2, but this is 5 to the power 2. This is a3, this is 5 to the power 3. Generalizing this, it seems that an is given by 5 to the power n. That is something else. The third item I need to take care of is the numerator. Look, this is 1, 3, 2, 4, 3, 5. So that is what? That is n plus 2. You can see this generalization. And now you can check your answer. You can check your answer by substituting back the integer values, the positive integer values. So if you substitute 1, this will be positive. This will be 3. This will be 5. So that's 3 over 5. Substituting n equal to 2, this will be odd. So this is negative. 2 plus 2 is 4. 5 squared, 25. So yes, it makes sense. It is moving fine. So this is the way you move from the general term given to list some elements. And this is another example where you have some elements given, and assuming this pattern is the same, will continue, you can find the general term. So you can write the sequence now as minus 1 to the power n plus 1, n plus 2 divided by 5 to the power n. So this is just an example to illustrate the meaning of a sequence. and how to move from one form of a sequence to another form, meaning from one notation to another notation. But what does it mean, the limit of a sequence? What does it mean, a limit of a sequence? Let us try to get an idea about this and then write the precise definition. Before I go to the precise definition, let us take an experiment. For example, so this is the question we need to answer. What is a limit of a sequence? If I am given a sequence, what do you mean by limit of that sequence? To understand this idea, let us take some examples first, then try to write the definition. I start with simple exercise here. Now assume someone gave me the nth term to be an is equal to 1 plus 1 over n. And he asked what is the limit as n goes to infinity? What happened to these values as n become very large? N goes to infinity. Okay, that's what we need to investigate. Okay, let us try to plot some points from the sequence and see what are the values. So here I will draw n, and here I will draw a n. Okay, so what do we have? For example, I have n equal to 1, so this is 1, n equal to 2, this is 2, n equal to 3, this is 3, n equal to 4, this is 4, n equal to 5, and etc. Okay, let us see this. If you allow me, I will draw a line here just to help me to graph these points. I will draw this line to be y equal to 1. This is the line. This is the line y equal to 1. Okay, why am I drawing this? This is y equal to 1 or L is equal to 1. Let us say this is, okay, this is y equal to 1. Okay, fine. Let us look for these points now. Of course, if we have a sequence defined only over integers. So if I plot at x at n equal to 1, I have 1 plus 1 over 1, that's 2. So this is exactly what we have here. Let us say this is 1 and 2. So it is a point here thrown. A second point at n equal to 2, this will be 1 plus 1 half. 1 plus 1 half is somewhere here. It is 1.5. So let us say something like this. N equal to 3 will be 1 and 1/3. So it's coming closer and closer to 1. N equal to 4 will be less than this for sure, and so on. Assume, for example, we are moving up to, let us say here, n equal to 1,000. Okay? If n equal to 1,000, what happened? This will be what? It will be 1 plus 0.001. That is 1.001. 1.001, so almost you are here. So imagine now, if n goes to infinity, so if this one is 1 million and so on, this became, the quantity become closer and closer to what? To 1. So formally, now we will say, it seems that if this n goes very large, goes to infinity, this sequence is approaching the number 1. Not yet, this is the definition, but we are trying to understand here the meaning of the limit. So we are motivating to move to the what we call the precise definition of the limit of a sequence. For this specific exercise, we can see now as n moves large enough, then all these points will be closer and closer to what? To the number 1, as close as we want. So we say in that case the limit of this sequence is equal to 1, and we write the limit as n goes to infinity of the sequence an, which is given by the limit as n goes to infinity of the sequence an, that is 1 plus 1 over n, that is equal to, we say it is equal to 1. Let us see more type of sequences and try to figure out whether it is convergent or divergent, formally speaking. Then we go to the precise definition of the meaning of what? The definition of limit of a sequence. Now let us see the second sequence. Now I call it, for example, here number 2. Let us take and consider this sequence, minus 1 to the power n. This is very interesting sequence, minus 1 to the power n. Let us study its behavior. And then, formally speaking, we can deduce something about convergence and divergence, let us say. If we plot some points here, some points for n, some points for f of n, okay, what do we have? Let us take some points in the integer. So let us say 1, this is 2, this is 3, this is 4, etc. Okay, at n equal to 1, this will be minus 1. So the point will be here somewhere. Let us say this is minus 1, this is 1. So this is the point here, minus 1. At n equal to 2, you can see this is minus 1 to the power 2. That is 1. So somewhere it's upstairs here. So it's 1. 3, it will be minus 1. 4, it will be 1. 5, it will be minus 1. 6, it will be 1. So what happened for this kind of sequence? You can see now the values are oscillating between 1 and minus 1. So what happened as n goes to infinity? Still the same behavior will be there. Still the values, if n is odd, it will be minus 1. N is even, it will be 1. As n goes large enough, again, you have the same behavior. So what's happening at the end? We have infinitely many points equal to 1. We have infinitely many points equal to minus 1. We cannot claim that the limit is equal to 1, and we cannot claim that the limit is minus 1. We call it in this case oscillating sequence. It is oscillating between minus 1 and 1. So it has infinitely many points equal to 1 and infinitely many points equal to minus 1. Mathematically speaking, we say this sequence has a subsequence goes to 1, another subsequence goes to minus 1, and these two subsequences do not go to the same limit. So simply we say this sequence is not convergent, or we say it is divergent. So we will say this limit now, limit as n goes to infinity minus 1 to the n does not exist. Why? Because it behaves like oscillating between 1 and minus 1. They call it oscillating sequence. So the limit does not exist. It seems that if you go to infinity, this limit does not go to a certain number. It's not approaching a specific number. We cannot be as close as we want to a specific number by choosing insufficiently large. Okay. Maybe someone will think that because we have a minus 1 to the n oscillating behavior, so the limit always does not exist. Still, I'm talking formally about the meaning of what? The limit of a sequence. Not yet I defined precise definition of limit of a sequence. What we are doing now is just to tentatively talk about the meaning of limit of a sequence. So let us take a third experiment here. It's minus 1 to the n, yes, but I will divide by n. And we will see this behavior of the sequence. Is it going to a certain number, or it oscillates also like before? Okay, fine. So let us go and draw some picture. So draw some points, sorry. This is n. This is a n or f of n. It's whatever. We call this one f of n. It's supposed to be simply a n. Okay? So let us say this is 1. This is 2. Again, this is a 3. This is 4. And we move like this. 1, 5, and so on. So at n equal to 1, this is minus 1 to the power 1. That's minus 1 over 1. That's minus 1. So yes, we are here. At n equal to 2, this is positive, and if this is 1, so it will be 1/2 somewhere here. Okay? At n equal to 3, this is negative, yes, but it is less than this. So it's somewhere, if this is 3, so this is, let us say, if I erase this one, sorry for that, this will give you 1/3 somewhere here, minus 1/3. If n equal to 4, this is positive, 1 over 4, so it's closer than this, it's somewhere here. N equal to 5, also closer and closer, but negative. And what's happening to these points? You can see, we start at minus 1, then 1/2, then minus 1/3, then 1/4, then 1 over 5. So just imagine now what happened if this is, for example, like 1,000. It will be minus 1 to the power 1,000, that is positive 1,000. So it is 1 over 1,000, that is 0.001. Okay, fine. If this is like 1 million, what's happening here? It will be 0.005 times then 1. Yes, we have sometimes positive, sometimes negative, sometimes positive, sometimes negative. But the behavior of the sequence, it seems that both sides are approaching the same value, which is what? Which is 0. In this case, we say the limit as n goes to infinity of minus 1 to the n divided by n is equal to 0 because they are approaching 0. But the question now, this is formally speaking the meaning of limit, but what is the precise definition of a limit? That will be our next definition. Now, what is the meaning of a limit of a sequence precisely, mathematically speaking? It says a sequence an, if we are using this notation here, of course, we mean here n is equal to 1 up to infinity. An infinite sequence has a limit L, This is the limit of the sequence. And we write, this is the notation for the limit of a sequence. So we say the limit of an as n goes to infinity equal to L, or sometimes we just write an goes to L as n goes to what? Infinity. Well, now let's look here carefully. It says if for every epsilon greater than 0, there is a corresponding integer n such that an minus L less than epsilon whenever n greater than n. What does it mean? First, we need to understand why they said corresponding integer n. Corresponding integer n because different epsilons will give you different integers. So this integer n here corresponds to what? Epsilon. It depends on epsilon. What is epsilon actually? Epsilon is a distance from the number we claim that the sequence is converging to. For example here, if we claim that the limit is L, so we claim that the distance between the elements of the sequence and L can be made less than epsilon whenever n greater than n. What does it mean? Now let us see what does it mean here. Okay, if we just draw something like this, for example, and we said this is our L. This is our L that we claim that the limit is approaching, okay? The challenge is here. If someone gave me any epsilon distance around L, any epsilon distance from L, I can always find an integer n, capital N, okay? After which, all elements of the sequence will be located within an epsilon distance of L, okay? Regardless of how small is this distance, I can find an integer n. The images of all points after that number supposed to be within this distance he gave me. Let us look at it from another direction. For example, the meaning of this is like this. If you assume that this is your L, okay, and assume someone gave you an epsilon distance around L, okay, fine. This is L minus epsilon, and this is L plus epsilon. The definition says we don't care about finite number of elements. You may have this few elements somewhere outside, outside this interval, maybe here, there, whatever. But starting from a specific integer n, no way. All elements will be in this portion of the graph. Look, we have strip here moving. Okay, we may have finite number of terms outside, we don't care. Starting from this end, all points should be located somewhere here. Okay, of course this point will be closer and closer to that number, regardless of how small this epsilon is. Maybe if you have one epsilon, let's call it epsilon 1. Then it will give you a specific integer, after which all elements are inside. But if someone made this epsilon much smaller, for example, you are coming closer to L, you may find another integer n2, for which all points will be what? Will be inside that strip. Let's do this definition. Let's apply it in our previous examples here. Let us look here, for example. We claim that the limit of this sequence is equal to 1. That's our claim, isn't it? So, the question is, if someone gave me, for example, epsilon 2p, for example, 0.1, okay? So, I can move 0.1 from 1, so this will be 1.1, this will be 0.9. This is 1.1, this will be 0.9. Can you find an integer? This is the challenge now. Can we find an integer n for which all elements after that integer will lie inside this small strip? The answer is yes, we can do that. We can choose in this case our capital N to be what? To be 10. If we choose our N to be 10, this will be 1.1. After this, all elements will be inside this strip, right? Because what happened after N equal to 10? N equal to 11. This is less than 1.1. Okay, after N equal to 10 means N equal to 12, N equal to 13, N equal to 14. So starting from 10, after this number, which is our capital N equal to 10, all elements will be inside this small strip we are drawing now. All elements will be inside here. Okay, so yes, in this case, we say the limit is equal to 1. But someone said, no, I will change my epsilon here. I will make it 0.01. Can you still find an integer here correspond to this? The answer is yes. Let me keep the choices so that you understand the meaning of corresponding integers. So I will say here, let me do it this way. I will say for epsilon is equal to 0.1, we choose our N to be 10, okay? But if epsilon is equal to, let us say, 0.01, can we find an integer so that the distance from 1 is, okay, after N equal to that integer, all points will be in a strip of distance 0.01 of 1. So this is 1. If you say 0.01, so this distance will be now much smaller, okay? So this strip will be narrower, in other words. So let us say I'm ignoring this, so these elements will be what? These 2 points will be, okay, somewhere it's closer here, so let's say this point 1.01, and this is 0.99. So we are coming closer and closer to 1. Okay, fine. I can still do that. I can choose our N to be 100 here. If you choose N to be 100, look here. If you choose it exactly 100, this will be 1.01, so we are at the borderline, 1.01. But after that, what happened here? N equal to 101, 102, 103, up to infinity. 1 plus 1 over something greater than 100 will be for sure less than 1.01 and greater than 1. So we are exactly inside this small strip, if you like. If you continue like this, okay, sorry for that. This is just a line which is moving close to 1. And this is another line that is moving close to 1. And you are sure after N equal to 100, you are inside. Okay, let's do one more. If epsilon is equal to 0.001, of course we need to take larger N, yes. So in that case, I will choose my N to be 1000, okay? Because exactly at 1000, this is at the borderline of 0.001 distance from 1. After that, all points will be located inside and so on. So you can see now there is what we call correspondence here. You have epsilon, you need to find N. You have another epsilon, another N. A third epsilon, a third N. So N is corresponding to what? It depends on your distance chosen. So epsilon will give me N. N is corresponding to epsilon. That's what it means here, a corresponding integer N. And I will summarize now by saying that for sequences, infinite sequences, we don't care about the few terms at the beginning. I mean by few terms, any number of finite number of terms. We need the behavior to be close to a certain number starting from a specific integer. This could be 100 after 100 terms. It could be after 1000 terms. I don't care. After finite number of terms, I need all points to be located close to a certain number in order to say that the limit is equal to that number. Let us do the same for our second example. We did it formally. Now we will do it precisely. If someone says, okay, you have now many points, 1, 1, 1, many points, -1, -1, etc. Now, if someone claims that the limit is equal to 1, this is -1 and that's 1. If someone claims that the limit is equal to 1, I will tell him, okay, can you take epsilon to be 0.5, which is large enough even. So this will be 1.5 and this will be 0 for sure. This is 0. Can you give me an integer N after which all points will be in this interval? Impossible. Because whatever n he gave me, I can choose an odd number after that integer whose image is equal to -1, which is outside the interval. And similarly, you can, if someone claimed that the limit is equal to -1, I can choose any epsilon here around these points, okay? And I ask him, okay, can you give me an integer n for which all points after that will be located in this specific interval? And he will not be able to do this. Why? Because we have, after any integer, an even integer that give me the image is equal to 1, so it is not located inside the interval here. So in that case, we say the limit is not equal to -1. For this exercise, we have oscillating, as we said, and it does not exist, or the limit we cannot find a specific limit for the sequence. Okay, fine. What about this one? -1 to the n. -1 to the n, we claim here that the limit is 0. Now let us check if we can choose for any epsilon greater than 0. We can find an integer after which all points will be located. This is very simple here. Give me any epsilon you like, okay? If you take any epsilon around 0, so this will give me a distance here, right? Let us choose a specific one, for example, 0.1. So this will be -0.1, that is 0.1. If you choose epsilon equal to 0.1, I can choose for you n to be what? N to be 10. Our capital N in this case will be 10. After 10, the 11th term, the next one, after 10, all of them will be inside the strip. If he said, no, I will choose, let us say epsilon equal to 0.01, I need to move further. So I need to go up to, for example, the 100 terms. I'm sure after that, all points will be located in that interval. If you choose epsilon to be 0.001, I need to go further. I need to go up to 1,000. So I need larger n as epsilon became smaller. So this is the meaning of correspondence between epsilon and the integer n. Okay, that's the precise definition of the limit of a sequence. Now what is next point? We are interested basically in finding the limit of a sequence. So we will talk about some theorems and techniques to evaluate the limit of a given sequence. After we understand now the meaning of the limit, how to find the limit, that is the most interesting part we need to discuss in this talk. Okay. Now let us discuss some theorems that will help us to find the limit of a given sequence. The first theorem of interest is this. It says, if the limit of f of x as x goes to infinity equal to L, and you have the function agrees with the sequence at the integer points, where n here is an integer, okay, is an integer number, okay, then the limit of an as n goes to infinity is also equal to L. What does it mean? Okay, if we have a function, you know what is the difference between functions and sequences. Sequences are defined as discrete points. These are points defined only over integers. But functions, you know, functions, they have different domains. You may have like the domain is 0 to infinity, but in that case we mean 0 to infinity. This is an interval. So it's defined at each real number, I mean rational or irrational, integer or not integer. Okay, the question like this, it says, assume for example, for instance, you have a function that is decreasing up to 0 as x goes to infinity. Let us take for example y equal to 1 over x, okay? Now, if you look for y equal to 1 over x, and if I choose another color here for another one, if I take a n to be 1 over n, what is the relationship between these two things? For this, of course, if I'm considering only the positive part here, the domain of it is 0 to infinity. Actually, the domain is from minus infinity to 0, but we are comparing only after 1. So I'm considering only the 1/2 of the domain here. If you just substitute these points, 1, 2, for the x values, 3, what do we have? Here we have a point that is called A1. Here we have a point that is called A2. Here we have a point that is called A3. Now, if we can use our previous knowledge in finding the limit of the function as x goes to infinity, this theorem says you can use your own previous knowledge to also calculate the limit of the sequence. Why? Because if this function and this sequence are the same at the integer points and the function is approaching certain number, then for sure these points also will approach the same number. Someone will say, okay, what is the benefit of this? We can easily answer this question by saying that the benefit of this, you can use all the tools you learned in calculus 1 in order to find the limit of a function, and simply you can deduce the limit of the sequence. That is very interesting. What is the second theorem now? This is the first theorem. The second theorem says, okay, do we have a squeezing theorem for sequences? We had squeezing theorem for functions. Okay, now yes, we have this. It says if you have 3 sequences, an, bn, cn, and you know that this is inequality holds true for all points after again some finite number integer point in 0. And you know that the limit of the first sequence and the limit of the last sequence here go to the same number L. Then what can we say about the middle one? The middle one is also goes to the same limit L. The beauty of this, and the thing that you need to take care of, is what does it mean that this is inequality hold true, after some, or enough to have it after some n greater than or equal to n0. It means you don't need to have this inequality to be hold true starting from n equal to 1. Not necessarily. You may have A1 is larger than B1. C1 is smaller than A1 and B1. We don't care. You may have the first 1,000 terms are not arranged at the same order here. But we need this inequality to be hold true, starting from a specific integer n up to infinity. If it is there enough to deduce the result here, that is the limit is equal to. So simply, we don't need it to be true from the beginning, but we need it to be true after some while. If it is from the beginning, that is okay. If not, enough to have it organized in this way after some integer n0. That's what it means. Okay, next one. So we call it squeezing theorem. We will use it also. A third theorem of interest is this. That says if the limit of the absolute value of the sequence is 0, then for sure the limit of the sequence itself is equal to 0. How to prove this? Simply how to prove this theorem using the previous theorem. Okay, we know that any real number is less than equal to greater than equal to. It's always less than its absolute value, and it's always greater than its minus or the negative of its absolute value. This is always true for any n, for any integer n. Okay, what can you say about the limit of this? This is given to be equal to 0, right? This is given to be equal to 0 by the condition we have. It says if the limit of the absolute value is 0. Fine. What about the limit of this? Also it goes to 0. Why? It's constant times this. Constant, you can take it outside the limit and still it is going to 0. That's convergent sequence. So what can you say about the middle one? By squeezing theorem. By squeeze theorem, what do we have? By squeeze theorem, also we have the limit of a n is equal to 0. We should be careful here, because the theorem says if the limit of absolute value is equal to 0, not any number different from 0, not any number different from 0, then the limit is equal to 0. For example, if I gave you minus 1 to the n, the example we did, if you take absolute value, that's always equal to 1, and the limit is equal to 1. Does it mean that the limit also of the original one is equal to 1? No! That's only true if the limit of the absolute value is equal to what? Is equal to 0. Then we can apply this theorem. Now let us use these theorems and techniques we did in calculus 1 to find the limit of different type of sequences. This is the first one of them that says, okay, find the limit of each of the following limits if it exists. Okay, What is the limit of this? Now, techniques we did in calculus 1 says if you have a rational function, the only thing you need to do is to divide by the largest power in the denominator. Okay, fine. The largest power in the denominator here is n squared, so I would say this is 3 minus 1 over n squared. That is 1 plus 2 over n squared. Then we need to observe that as n goes to infinity, this quantity goes to 0, this quantity goes to 0, so this goes to 0, this goes to 0, so that is 1 over 3. So we say the limit of this is equal to 1 over 3. 1 over 3. Okay? So that is the limit as n goes to infinity. More examples. Let's talk about part B. Consider this sequence and try to find the limit as n goes to infinity of ln n over n. Okay, fine. Ln n over n. As n goes to infinity, this goes to infinity and this goes to infinity. So it is infinity over infinity. Okay. Can we use Hopital's rule to find the answer? Can we use the Hopital's rule to find the answer? Okay. If we need to use Hopital's rule as a tool, we need differentiability. But do we have differentiability for sequences? The answer is no. That's why this theorem is important here. So what should we do then? Okay, let the function f of x defined to be ln of x over what? X. Ln of x over x. And note that what? What do we have here? F of n is exactly equal to what? The images of the function at n, the integer points, the positive integers, is exactly equal to our sequence then of n over n. So, what is the benefit of this? No, we have great benefit now that says, if I need to evaluate the limit of the sequence, it's enough to evaluate the limit of the function as x goes to infinity. So, what should I do? Instead of evaluating the limit of the sequence, I will evaluate the limit as x goes to infinity of ln of x over x, which is infinity over infinity. So I will use Hopital's rule here to find the limit. So the limit as x goes to infinity, and I differentiate. I will have 1 here. I will get here 1 over x, and clearly this goes to what? This goes to 0. What is the bridge now? If the limit of the function goes to 0, so the limit of the sequence also goes to 0. By the theorem there we have, it says this implies also the limit of the sequence as n goes to infinity of ln n over n. Also, this is equal to 0 by our previous theorem here. Fine. What other types of sequences we have? So we consider different type of sequences. Okay, let us talk about this specific one here. So this is part C. We are considering, okay, I'm considering here a sequence of this form that says find the limit of the sequence e to the n plus e to the power minus n divided by e to the power 2n minus 1. Okay, as n goes to infinity. This is what we have here. So what is the limit of this sequence as n goes to infinity? What is the limit of the sequence as n goes to infinity? Simply, if you can just substitute, let n goes to infinity. We have something here, e to the infinity, that is infinity. This is e to the power minus infinity, which is 0. This is e to the power infinity minus 1. So again, we have sort of infinity over infinity. You have two options here. Either you differentiate or define a function, and then differentiate, or you can simply do the following here. What I will do for this specific exercise, I will divide by the more significant term in the denominator, which is e to the power 2n. E to the power 2n, if I divide by it, I will have here 1 minus 1 over e to the power 2n. Then in the numerator, if I divide by e to the power 2n, what do we have? I have e to the n divided by e to the power 2n, that is e to the power minus n. Okay? Plus, if I divide by e to the power 2n, I will have here e to the power minus 3n. Fine. Now, as n goes to infinity, what do we have? As n goes to infinity, what do we have? As n goes to infinity, this goes to 0. Okay? And also this goes to 0. And as n goes to infinity, also this goes to 0. So what we have is 0 plus 0 over 1. And that is again equal to what? Equal to 0. Interesting. Now let us do one slight modification for this exercise. What happened if I multiply this, all of it, by minus 1 to the n? I call it part D. I leave it for you to think about. This is n goes to infinity minus 1 to the n times e to the n plus e to the power minus n divided by e to the power 2n minus 1. That is not a difficult one. Okay, so this is equal to 0. Let me say like this. This is equal to 0. What about this one? Yes, we can take the absolute value here. If you take absolute value, you are back to this. And if you are back to this, you can use this theorem here that says if the limit is equal to 0, then the limit of the sequence itself is equal to 0. So that is a direct application for the third theorem we have here. I leave it for you to write the answer. It is just 0. It is again 0. Okay. Next, how to deal with the factorial. Okay, how to deal with factorials. So this is what we have. Before I go to factorials, let me add one more exercise about this theorem here, just to see the difference of two things. The first one, let's call it part E. This is part E, okay. If we have something like this, what is the limit as n goes to infinity? And that is minus 1 to the power n. This is n over n squared plus 1. What is the limit of this sequence as n goes to infinity? So one trial will be like this. One trial will be, okay, why don't we take the absolute value of the sequence, absolute value of an, if you call that one an, then this will give me what? That will give me n over n squared plus 1. Then what is the limit of the sequence as n goes to infinity of n over n squared plus 1? Simply this is equal to the limit as n goes to infinity dividing by n squared up and down. This will be 1 plus 1 over n squared. And that is 1 over n. Of course, this will be equal to 0 because this is 0, 0, 1, 0 over 1 plus 0 is equal to 0. What can we conclude now? The limit of the absolute value is equal to 0. The limit of the absolute value equal to 0. Then the limit of the sequence is equal to 0. So we can conclude now, we can conclude that the limit of the sequence itself also, the limit of the sequence also, minus 1 to the n multiplied by n divided by n squared plus 1 is also equal to 0. That is one application for the third theorem. The question is this, before I go to factorial again. What happened if we take the absolute value and it happened that the limit of the new sequence is not 0? What can we conclude from that? I will give you some more examples to illustrate this idea, then I move to the factorial stuff. Look for this, another exercise, or interesting one, that is, what is the limit as n goes to infinity? I will say here minus 1 to the power n, the same exactly. I will just do slight modification, n squared over n squared plus 1. It seems questions are similar. Yes. Do we have the same final answer? We'll see. What should we do? If someone said, I will do the same, so I will take absolute value of an, and that is nothing but n squared over n squared plus 1. Okay? This is what we have. Fine. The question is, what is the limit of this as n goes to infinity? Limit of this as n goes to infinity of n square plus over n square plus 1, simply this is equal to what? This is equal to 1. The question is, can we say that the limit also of this sequence is equal to 1? Does the theorem say this? No. The theorem says if the limit of the absolute value is 0, then the limit of that one is equal to 0. But it doesn't say that if the limit is 1, then the limit of the original one is also equal to 1. So what is the limit of this then? Look at it from this point of view. Forget about minus 1 to the n. This expression as n goes to infinity is approaching 1. Together with minus 1 to the n, that will make it what? Oscillating between minus 1 and 1. So what can you say about the limit in this case? We say the limit does not exist. This is one way to say it. Another way to say that, we have a nice theorem that says if a sequence is convergent, if and only if all its subsequences converge the same limit. Meaning, for example, if you take this specific one here, minus 1 to the n, then you can construct two subsequences. For example, if you take n to be even, then this will be just n squared over n squared plus 1. Meaning, I can rewrite an like this. It will be n squared over n squared plus 1. This is if n is what? An even number. An even number. So let us say simply, this is, sorry for that, this is even. Okay? And it will be, if n is odd, this is minus n squared over n squared plus 1. This is true for any n that is what? Odd. So, considering this one as a subsequence for all even terms, and this is a subsequence for all odd terms, you can see easily that this goes to 1, this goes to minus 1. Since they tend to go to different limits, we can conclude that the original sequence is not convergent, it is divergent. Actually, it has an oscillating behavior now. So we look at this from two points of view. We said either we construct two subsequences, and since these subsequences converge to different limits, so this one does not exist, or we say, okay, the limit of the absolute value is not equal to 0, together with minus 1 to the n, that makes a oscillating behavior. So the final answer is this limit does not exist. The limit does not exist. It is an oscillating sequence again, by the two discussions we made. Okay, fine. Let's move to the other type of sequences, which is a sequence involving factorials. So let me just separate this one as a separate exercise. I mean, different exercise here, but it's asking about limits again. Okay, interesting here. Let us talk about this sequence. Find the limit as n goes to infinity of whatever we have here. Maybe I will write 2n plus 1, something like this, factorial divided by 2n minus 1 factorial. If we have factorials, what does it mean, factorial? If I say this is, let us say, 5 factorial, what does it mean? It means it is 1 times 2 times 3 times 4 times 5. We stop up to 5. So it's the multiplication of the integer, positive integers from 1 to 5. If I say n factorial, what does it mean? It's 1 times 2 times 3 times up to what? N minus 1 up to n. We need to play with this factorial. Always, I can rewrite this one as 5 times what? If I stop here, this will give me 4 factorial. If I am interested to stop at 3, I will say this is equal to 4 times 5 times 3 factorial. Similarly here, I can rewrite this one as n minus 1 factorial times n. I can say this is equal to n minus 2 factorial times n minus 1 times n. So always we can simplify factorials this way. Let's try to do it here. Okay, this is 2n minus 1 factorial like this. Fine. So what should we do? I will rewrite this as n goes to, of course here I cannot define a function because we have the factorial here. So what should we do? We need to simplify. So I keep 2n minus 1 factorial. So I start with the larger one. 2n plus 1 is larger than 2n minus 1. I start with that and try to simplify. So if I separated the first term here, what do we have? We have 2n plus 1 times what? 2n plus 1 minus 1. That is 2n factorial. Now I need to move one more. So let me write it here first. 2n plus 1 factorial is equal to 2n plus 1. I'm separating the last term times 2n factorial. Subtracting 1. Move one more step. Do the same for this. You can separate 2n. What is the preceding term? 2n minus 1. So it is 2n minus 1 factorial. So that's exactly what I will do now. I will multiply by 2n. This is 2n. So I'm just rewriting the same thing here times 2n minus 1 factorial. Okay? And you can now easily see that this will be cancelled out. So what happened as n goes to infinity? Of course, this is going to infinity. This is going to infinity. The multiplication also goes to what? Infinity. So the limit again does not exist. It will go to infinity. That is the way we deal with factorials. Okay, fine. I will do one more exercise. We have plenty of exercises about limit of sequences. One more for this part about factorial also. That says, okay, the question here, of course, this is an example and it says find the limit or discuss the limit of the convergence of this. Since we are talking about factorials, let me call this one part A and give you another part here, that's part B, which is of interest here. It says find the limit as n goes to infinity of whatever we have here. That is n factorial over n to the power n. Okay, n to the power n. N factorial n to the power n. So what is the answer for this? What is the answer for limit of n factorial over n to the power n? Again, we cannot define a function, so the only way we can deal with this is the following. We will try to use the squeezing theorem. So what I will do here, what is n to the power n? It's n times n times n times, let me write one more, times n times. This is n minus 1, this is n minus 1 times. So we have up to n. How many times we have here? This is the multiplication n times. Okay, that's one thing. The second, what is the meaning of n factorial? N factorial is 1 times 2 times. So it's multiplication of n elements, but this is okay for this is n minus 1 up to what? Up to n. That's exactly what we have. Let us look carefully for this expression here. Of course, this expression is greater than 0. Okay? This expression is greater than 0. Look for these terms. Let us look for these terms. Okay, let us look for the terms from 2 up to n divided by n by n by n by n. Okay, fine. N over n, this is equal to 1. N minus 1 over n, this is less than 1. N minus 2 over n, less than 1. 3 over n, less than 1. 2 over n, less than 1. I am multiplying 1 over n by a number that is less than 1. So which one is larger? Of course, this will be smaller than what? Smaller than or equal to 1 over n. Why? Because I'm multiplying a positive number by something less than 1, so it will be smaller. So this is smaller than this. For example, if I multiply 3 by a number less than 1, let us say 1/2. Which one is larger? 1/2 times 3 or 3? Of course, 1/2 times 3 is smaller than 3. If you multiply, for example, 5 by a number less than 1. Let us say 1/4. Compare it with 5. Which one is larger? Of course, 5/4 is smaller than 5. So if I am multiplying a number by some number less than 1, I get something what smaller. So this is smaller than its original. So something here. Same thing here. I am multiplying 1/n by a number which is less than 1. So for sure, this is less than 1/n. Fine. I get a bound now for the sequence I have. Good. What can you say about the limit of this as n goes to infinity? 0. What can you say about this one as n goes to infinity? Also, it goes to what? 0. What can you say about the middle one as n goes to infinity? Now we say by squeeze or squeezing, it's up to you. By squeezing theorem, what do we have here? By squeezing theorem, the limit of the sequence as n goes to infinity of n factorial over n to the n is also equal to 0. Fine. These are two examples about factorials, and this is the way we can deal with factorials to evaluate limits. I have another point now, which is, of course, we have different types of limits and different techniques you can use to find the answer for different types of limits. Let us add one remark, and then we move to the meaning of monotonic sequence, increasing, decreasing, and bounded sequences, and what is the relationship between monotonic, bounded sequence, and convergence. That will be our last point. Before I go to that last point, I have something to say about this. So I need you to note this remark, and the remark says, what is the limit here as n goes to infinity of r to the n? I will say this is equal to, look, what happened if r exactly equal to 1? If r exactly equal to 1, this is equal to 1. So this is if r is equal to 1. Now, so this is the real line like this we have, okay? And we are considering now r is equal to 1. So r equal to 1, it gives me 1. So, okay, we have another thing now. What happened if this r is between -1 and 1? -1 and 1. If it is between -1 and 1, let us take first the positive and then say something about the negative one. So, if the number r is less than 1, r to the n is decreasing function, right? So what is the limit of r to the n as n goes to infinity? We have the exponential function. This is a positive number less than 1 raised to the power n. So it is decreasing, decreasing, decreasing. So it goes to 0, okay? This is if it is positive, if r is positive. For example, 1/2 to the power n. As n goes to infinity, this goes to 0. But what happened if we just put a minus sign? So it's -1/2 to the power n. That's very interesting. If you take absolute value, you will be back to this, r to the n, and r is between 0 and 1. So again, it will go to 0. Why? Because the absolute value goes to 0, so the original one also goes to 0. If you take absolute value here, you are back here, 1/2 to the power n. 1/2 to the power n goes to 0, so this one also goes to 0. So the answer is always 0 if we have r between -1 and 1. More than this. What happened if r is greater than 1? If r is greater than 1, take an example, 2 to the power n. What happened as n goes to infinity? This goes to what? Infinity. So it is divergent. If r is less than -1, also this is -2 to the power n, for example. It is also what? Divergent sequence. So what is the conclusion now? After all of this, we can say that this sequence is convergent only if r between -1 and 1 close from 1, and it is divergent otherwise. So this sequence is convergent if we have r is greater than minus 1 but less than or equal to 1, okay? If r is equal to minus 1, we have minus 1 to the n. That is the oscillating sequence we have. So it is if r is between minus 1 and 1 and divergent if what? If we have absolute value of r is, let us say, greater than 1. It is divergent for r greater than 1 and what? Less than minus 1. So let me say it this way. If this is divergent, if r is greater than 1 or r less than or equal to what? Sorry, this is r is less than equal to minus 1. This will be more precise here because once we said absolute value of r greater than 1, we are ignoring x equal to or r equal to minus 1. This is r to the n is convergent only if we have this, or r specifically is equal to 1. It's divergent for r less than minus 1 or greater than 1, less than or equal to minus 1 or greater than 1. The next point, as I said, we'll be talking about what we call monotonic sequence, bounded sequences, and the relationship between these two terminologies and what we call convergence. Stop for today. Yeah. Now, after we saw how to calculate the limit of a given sequence, what does it mean? Increasing sequence, decreasing sequence, monotonic sequence, and bounded sequence. Okay, starting with the first one. So a sequence, a given sequence, for sure an is called decreasing if an is greater than an plus 1, meaning the values became smaller and smaller as n is increasing. For this is true for all n greater than equal to 1. And it is called increasing if an is less than an plus 1, meaning the values became larger and larger as n is moving for all n greater than equal to 1. In both cases, increasing and decreasing sequences, these sequences are called monotonic sequences. So monotonic means is a sequence that is either increasing or decreasing. Both of them, they are called monotonic sequences. Okay, how to show a sequence is decreasing? This will be explained in the following exercise. So the exercise will show that these two sequences are decreasing. Show that this sequence is decreasing. Also show that this sequence is decreasing. How to show a sequence is decreasing? We need to show, this is what we need to show, that an is greater than an plus 1. To do so, we have different ways. Either we subtract and see that is the difference is greater than 0, okay? Or we divide an by an plus 1 and show it is greater than 1. That's an alternative way to do it. Okay, for this specific exercise, what is an? What is an plus 1? What is an? An is just 3 over n plus 5, okay? N plus 5. That is the expression here. What is n plus 1? N plus 1 is just replacing n by n plus 1. So what do we have is 3 over n plus 6. We need to compare these two things. We need to see which one is larger. But it is very clear for us that n plus 5 is clearly less than n plus 6. This is true for any n greater than equal to 1. For all n greater than equal to 1, we have n plus 5 is less than n plus 6. So taking the reciprocal of this, these two positive numbers, so we will have n plus 5 is what? Larger than 1 over n plus 6. Why? Because we said the diameter, if it is larger, then the value is smaller. We can also multiply by 3, the inequality by 3. So what do we have here in the second or the next step? This one will be what? Would be 3. So what do we have here is just 3 is greater than 3 over n plus 6. 3 over n plus 5 is greater than 3 over n plus 6. And this is nothing but, this is equal to an, and that is equal to what? An plus 1. And by definition now, we see that an is greater than an plus 1. It means the sequence is decreasing. Okay, this is a simple exercise. Let us see another one. In the second exercise also we need to show that an plus 1 is less than an. This is what we need to show, and this is true for all n greater than or equal to 1. Okay, to see this, let us calculate an plus 1 and calculate an and see if we can say something about the difference between them. What I will do here, I will calculate an minus an plus 1. I need to show that this is what I claim this is less than 0. As an minus an plus 1, so this is what? Greater than 0. We claim that this is greater than 0. That's what we need to show. Okay, this will be greater than or equal to 0 if and only if I can say like this. Now what is an? An is n over n square plus 1, okay, minus what is this is an. What is n plus 1? This is n plus 1 all over n plus 1 all squared plus 1. If we can show that this is greater than 0, we are done. If we show that this is greater than 0, then we are done. But this is true only if and only if I will say this way: n over n squared plus 1 is greater than, let us look at this like n plus 1 opening or expanding this squared. We have n squared plus 2n plus 1 plus 1, that's plus 2. Again, this is true if and only if we have this is positive quantity, so we can multiply by n squared plus 1. Okay, so I will multiply this way. So what do we have is just n cubed. This is true only if and only if n cubed plus 2n squared plus 2n is greater than n plus 1 times n squared plus 1. That is n times n squared is n cubed. I have plus n squared, so it's plus n squared plus n, and finally I have plus 1. Okay, why this is possible? Because you know n squared plus 1 is positive quantity, so I can multiply first by n squared plus 1. Again, this is positive quantity, so I can multiply by this, so that way it's like I'm multiplying crossway. Fine. I delete n cubed plus and n cubed here. What do we have is this. This is if and only if 2n squared minus n squared, that is n squared. 2n minus n, that is plus n. And we have what? We have minus 1. For sure, this is greater than or equal to 0 for all n greater than or equal to 1. Why is that? Because the minimum value for this is at n equal to 1, which is 1 plus 1, 2 minus 1 is greater than. And this is increasing function, so as n is increasing, the value will be larger than 1. So for sure, this is always greater than 0. So moving backward, we saw that an minus an plus 1 greater than 0, meaning an is larger than an plus 1, so this one is decreasing. But you can see from the second part now, or the second exercise, that proving a sequence is decreasing, by definition, sometimes is not straightforward. So do we have an alternative way to prove the decreasing of the sequence? The answer is yes, if we can define a function. So in this case, I can prove this one by another method. Let me call it a second method here. So this is method number 2 to prove that this sequence is decreasing. And I will call this one method number 1. So since we introduce another method now, let's give some names for this. So this is method number 1. I apply the definition to prove that, okay, an is greater than an plus 1. Another way to do it, I will let a function f of x defined to be equal to whatever we have there, which is x over x squared plus 1. If I can prove that this function is decreasing after 1, so the sequence is also decreasing. Why? Because this function and the sequence agree at the integer points. So what do we have now? I will show that this is decreasing from 1 to infinity. So what I will do, I will use my tools of calculus. So I will find the derivative here. I discuss the derivative of the function. If you find the derivative of the function, this is what you have: x squared plus 1 all squared, okay, squaring the denominator. Then the derivative of x is 1 times this. So what you have is x squared plus 1. That is the derivative of the numerator times the denominator minus the numerator, which is x, multiplied by the derivative of the second one, that is 2x. This is what do we have. And this will lead us to the following expression, x squared plus 1 all squared. Now simplifying, I have x squared minus 2x squared, that is minus x squared. So we have here 1 minus x squared over x squared plus 1 all squared. Clearly now, you can rewrite this as, this is 1 minus x times 1 plus x, difference of 2 squares, and the quantity downstairs here is always positive, so I don't care about it. I care about these two expressions or these two factors. So what do we have is this. I have the critical points here, 1 and minus 1. So I have minus 1 and 1. And I will check the sign. I will check the sign diagram of the derivative function. So this is the derivative of the function, f of prime. Clearly, you can see that by choosing point after 1, point between minus 1 and 0, point before minus 1, you will have, this is negative here, and positive here. Okay, let us check at least one of them. For x greater than 1, this is negative, this is positive. So this is the multiplication is negative divided by positive, for sure it will be negative. So what does it mean? It means the function is decreasing here, 1 to infinity. If the function is decreasing from 1 to infinity, our sequence also is decreasing. Since our function here, f of x, is decreasing on 1 to infinity, okay, it's actually, you can even include 1 to infinity. This implies our sequence is decreasing, so our sequence an is decreasing for, okay, n greater than equal to 1. So that's the bridge we made here to use the calculus. We define a function, and we note that this function, when we substitute what is f of n is nothing but an. This is the note we need to take care of. That is the function and the sequence, they agree at the integer points. So whatever we can say about the function is also fitting with the conclusion of sequences by the theorem we did before. Now we define what is the meaning of increasing sequence, what is the meaning of decreasing sequence. And we said both of them are called monotonic sequences. Why this is important? We need to wait. We need to wait for the second now terminology, which is what? Which is the boundedness of the sequence. What is the meaning of a bounded sequence? That will be our next point. Okay, that's for monotonic sequences. What about bounded sequences? A sequence an, a given sequence an, is called bounded or is said to be bounded above if there is a number called capital M, this is a real number, such that all elements of the sequence is less than or equal to that number. In this case, we say M is an upper bound for this, or we say that an is bounded above by M. Similarly, it is called bounded below by small m, another real number, if an is greater than or equal to m. This is true for all elements, meaning for all n greater than or equal to 1. Okay. If it is bounded above and bounded below, then we say it is a bounded sequence. Maybe someone will say, why we are discussing the boundedness here and the monotonicity of a sequence? Do we have, a result for convergence here? Is any bounded sequence convergent? Is any monotonic sequence is convergent? Or no, we need more than this. Let us motivate this one by examples. Look for this sequence here. Okay, we have an, I define an to be just n. What can you say about this sequence? This sequence is increasing. Why? Because clearly an plus 1 is greater than an. This an is increasing. The question, what is the limit of the sequence? Clearly the limit of the sequence as n goes to infinity of n, this is infinity, so it is divergent. So being increasing as monotonic is not enough to say that this sequence is, convergent. Okay, fine. Another example. So the sequence is divergent. It is divergent. Fine. Let us take another example. This is let's call it 1. Let's call this one 2. Okay, we may have a bounded sequence like minus 1 to the n. You know minus 1 to the n is always between -1 and 1. All elements are greater than equal to -1 and less than equal to 1. So this sequence, the sequence here is bounded. The sequence is bounded. But the question is it convergent? We discussed this one before and we said that the limit as n goes to infinity of -1 to the n, this is a sequence with no limit, does not exist because it oscillates many times between -1 and 1. So we have, in other words, two subsequences. One of them is going to 1, the other one is going to -1. So we said the sequence is divergent. Fine. You see, we have an increasing sequence and the limit does not exist. So we have monotonic sequence and the limit does not exist. We have a bounded sequence, still the limit does not exist. So it is possible to have a monotonic sequence where we have no limit. It is also possible to have a bounded sequence with no limit. The question is, what happened if these two properties came together? We have a bounded sequence and in the same time it is monotonic. In that case, there is a nice result says, if a sequence is bounded, monotonic, for sure it is convergent. And that will be our next result. I will write now as a nice theorem here that says, no, if these two properties, the boundedness and the monotonicity of the sequence came together, you have for guarantee the sequence is convergent. So this is a very nice theorem that says, okay, if a sequence we have, which is called an, if this is both, we need both of them, both bounded, so we have the boundedness of the sequence, and at the same time, monotonic. What is the result? Then the result says it is, okay, sorry for that, it is what? Convergence. It is convergent. Okay? It is convergent. So if a sequence is bounded by itself, not enough. Monotonic by itself, not enough. But monotonic plus boundedness for guarantee, the sequence is convergent. Now, maybe someone will say, why do we need these two properties, boundedness and monotonicity? Why don't we go and calculate the limit directly? Okay, the previous examples we did with the theorems we had, we calculated the limit of a given sequence whose nth term is given. But this is not always the case. Sometimes finding the nth term of a sequence is not straightforward. In that case, we go to the alternative option. Or sometimes you have, sequences defined recursively. Terms defined by the previous terms. In that case, we need these two theorems to help us to prove convergence first. And then, since we have convergence, we will be able to find the answer. I will show you an exercise where these two theorems are important to calculate the limit of a sequence. And the exercise says like this. So this is the exercise. It says, show that the sequence defined by the following. It says, okay, it's defined by this. I have the first element here, a1 is equal to radical 2. Okay? And then I define the next term, an plus 1, recursively like this. It is square root of 2 times an. 2 times an. Okay, and this is of course true for n greater than or equal to 1. N greater than or equal to 1, meaning I can get a2 in terms of a1, a3 in terms of a2, a4 in terms, so it is defined recursively. Fine. The question says, show that this sequence which is defined by this is increasing. Okay? Not only this, then find its limit. Since it is Okay, prove it is increasing and bounded, sorry. It's increasing, bounded and increasing. This sequence defined by this, prove that this sequence or show that this sequence is, we need two properties we said. So is bounded and increasing. Bounded and increasing, then find its limit. Okay, let me say some words before I go to the example here. If I have a sequence, which is, let us say, bounded above by this capital M, and the sequence, let us say this is 1, something like this. It's starting here, then it is increasing, it's increasing, and it keeps the same behavior, increasing, increasing, increasing. It's enough also to say that this sequence, because it is increasing and bounded above, so it is for sure convergence. That is, a second part of the theorem here. Also, if we have a sequence which is bounded below by small m like this, okay? And we have the sequence is decreasing sequence, decreasing sequence, decreasing sequence, decreasing and bounded below. So for sure it is also what? Convergent. Okay, fine. The sequence we have here is actually bounded above and below. But we are interested in the upper bound of the sequence, or the, where the sequence is bounded, but what is the value of m that makes it bounded here. Okay, how to show this? We will prove this one by induction for one part, and the second part will be straightforward. So we have two things to be shown here: the boundedness and increasing. So let us start with the first one. Why this sequence is bounded? Step number 1, we need to show it is bounded, and then we will show it is increasing. Okay, how to show it is bounded? Showing it is bounded. Show it is bounded. I will show it is bounded above, because clearly here this sequence is a sequence of non-negative numbers, so it is bounded below by what? It's bounded below by 1, let us say, or by 0 at least. So for the lower bound we don't care about. It's bounded below by 0. It's also bounded below by 1, because this is greater than 1, and the next one, if we prove it is increasing, then it is also bounded below by 1. I don't care about that. I'm caring about, because if I can prove it is increasing, I need to show it is bounded above. That's enough. If it is bounded above and increasing, then I'm sure there is what? There is a limit for it. Okay, so is it bounded above? Well, I will start with the following claim. I claim that this one is bounded above by capital M, which is equal to 2. I claim now that all these points are less than 2. This is I will try to show. Okay, I have A1 is equal to radical 2. So this is true. The claim is true for n equal to 1. For n equal to 1, what do we have? We have A1 is equal to radical 2, and clearly this is less than what? 2. So the statement we wrote is true for n equal to 1. Now, I will assume that an is less than 2. Okay, let us say less than or equal to 2. It's less than 2. Okay, less than 2 or less than equal to 2. This is what we need to. Okay, we said it is bounded above by 2. So assuming this, we need to prove now that an plus 1 also less than equal to 2. Now, what is an plus 1? An plus 1 is radical of what? Radical of, this is what we have. An plus 1 is radical of 2 times what? 2 times an. But we know that an is less than or equal to 2 by assumption of the induction hypothesis. So what do we have? We have that this is less than equal to, okay, less than equal to 2 times, I will replace an by 2, because it is less than equal to 2. An is less than equal to 2. And the answer here is equal to what? It's equal to 2. So clearly we have an plus 1 actually is not even less than equal to. It is strictly less than this number. So I will say here, this is less than 2. So here I have an plus 1 is actually strictly less than 2. So what can we conclude now? This, by a mathematical induction now, this implies by By mathematical induction, we have what? We have an is less than 2 for all n greater than or equal to 1. Okay, fine. This is one thing. So we proved the boundedness. We saw that this sequence is bounded above by the number 2. Okay, what is next? I need to show that this sequence is increasing. The sequence is increasing. Why it is increasing? So what I need to do now, step number 2, I need to prove that it is the sequence is, I will say, increasing. The sequence is increasing. So how to prove it is increasing? I need to prove that an plus 1 is greater than an. An plus 1 is greater than an 4. So that's very simple here. What is an plus 1? An plus 1 is equal to, an plus 1 is equal to square root of, according to the definition we have, it is square root of what? Square root of, what is that? It's square root of 2 times an. Okay. But you can see here that this is greater than 2. 2 is greater than an for any n. This is what we proved. 2 is greater than an for any n. So this 2 is greater than an. So this is what we have here. It is just an times an. And clearly this is equal to what? This is equal to an. We have non-negative terms. Square root of an all squared is just an. So what do we have here is an plus 1 is greater than an. This is true for all n greater than or equal to 1. Okay. So what do we have now? From step number 1, we get that the sequence is bounded above. From step number 2, we have the sequence is increasing. By the theorem we have, since it is bounded above and increasing, then it is convergence. So from step number 1 and 2, the sequence is convergent. Okay, fine. Now what is the benefit of this? The sequence is convergent. The second part, he said, if it is convergent, then show it is convergent and find its limit. Since we know it is convergent, let us see how to find the limit of it. Okay, good. Now taking the expression for the sequence itself, we have an plus 1, we have an plus 1 is equal to square root of 2 times an. If the sequence is convergent, it means as n goes to infinity, the limit of an will go to a specific number called L, where L is a finite number. This is what is given here. Since the sequence is convergent, then this implies the limit as n goes to infinity of an must be equal to the limit as n goes to infinity of an plus 1 is equal to a finite number called L. That's what it means convergent, because as n goes to infinity, this goes to infinity, this goes to infinity. So we have the two, the sequence will go to the same limit, which is equal to L. So what does it mean? This implies L supposed to be equal to 2 times L. Solving this equation, we have L squared equal to 2L by squaring both sides. So this will give me L squared minus 2L is equal to 0. So this will give me 2 points here. We have L times L minus 2 by factoring is equal to 0. And this implies we have either L is equal to 0 or L is equal to 2. Of course, this is rejected. Why? Because we have a sequence whose elements are always greater than 0. Radical 2, 2 radical 2, and so on. Radical of 4, it is starting with radical 2, then radical of 2, radical 2, then radical of 2, radical of 2, radical 2, etc. So all of them are non-negative. So, positive strictly. So in that case, this one is rejected because at the end we cannot have the limit is equal to 0. So what is the final answer? The final answer, the limit is equal to 2. So what does it mean now? We have very nice sequence. Let me list some of these elements of the sequence. We have a sequence defined by this. I start with radical 2. Then the next element is what? It is radical of 2an. So it is 2 radical 2. Then the next one is radical of what? 2 times radical of 2 times radical 2. Okay? And so on. You move like this. And we prove that this sequence, which is defined recursively, is approaching 2 as n goes to infinity. Okay, let me summarize now what we have done in sequences. We define what is the meaning of infinite sequence. We took some theorems like the squeezing theorem, like if the limit of the absolute value goes to 0, then the limit of the sequence itself is going to 0. We have another theorem that says if you can define a function, and the function agrees with the sequence at the integers, the function agrees with the sequence at the integers, then if the limit of the function is equal to L, also the limit of the sequence is equal to L. We have also the rules of limits, like the sum of 2 convergent limit is the limit of the sum. The difference of 2 convergence limit is the limit of the difference, constant, multiple, etc. And then we move to the meaning of increasing and decreasing sequences, monotonic sequences, and bounded sequences. As a result of that, we have the nice theorem that says bounded monotonic sequences are convergent. These are the main points we have in sequences.